Hey everyone! So I thought it might be fun to teach myself some Python programming, and to help me do that I've been playing around with the Mandelbrot set. As many of you probably already know, the Mandelbrot set is that famous picture with infinite detail and an infinitely long border around a finite area. There are tons of videos on the YouTube showing very deep zooms of this shape, and they show the amazing details of this fractal way better than I'm going to show here. This is because my Mandelbrot sets will be cut out of paper. Here's how. First, I'll need the basic Mandelbrot set. It is generated by iterating each point in a given area on the complex plane through a function several times and testing whether or not the results are divergent. The function in particular is zn plus 1 is equal to zn squared plus c. And if the distance of z from the origin is never greater than 2, then the point on the complex plane is said to be inside the set. When you look at the Mandelbrot set, the black points inside the shape are the points inside the set, and the pretty colors we see around the shape are not in the set. Once I have the Mandelbrot set generating as an image, I then need to isolate each layer. I'll call a layer all the points on the plane that diverge within a given number of iterations. So for example, these are the points that we know will diverge after just one iteration, and then 2 and 3 and so on, up to 50. So let's say I printed one of these images out on paper and decided to cut out the shape with scissors where the black and white points meet. The scissors would have to travel along a path that runs exactly where the black and white points touch. But of course we aren't using scissors, we want to use a laser. The path that the laser has to travel is called a contour, and the solution to finding contours for any given data set is a handy-dandy thing to know how to solve in many different fields. One solution to this problem is called the marching squares algorithm. It basically works like this. Let's treat each of these images as a data set made up of columns and rows. Excluding the last row and column, we can run through each point in this matrix and look ahead one space in each direction. This will give us 4 points. Each corner of this square will either be black or white, so there are 16 possible combinations of these 4 points. And depending on these 16 possible combinations, we can assign one of 16 line segment options for each square. So running through every point on the black and white image and assigning the appropriate contour line segments for each one, we get a collection of line segments that, when viewed together, make up the contour line between black and white. We are not quite done with this step though, because it only results in an unordered set of segments with no beginning or end or direction. In other words, the scissors will jump around only cutting individual line segments instead of running through one continuous path around the shape. Originally I didn't do this step and my laser software was able to do it for me, but it took about 5 minutes of thinking before each image was able to get cut out on the laser. So I decided it's better to do it in the code. I need to run through all these line segments and put them together into one continuous ordered path. This is done by looking at each line segment start and end and grouping them by which ones touch and connecting them into a polyline with the correct order and direction needed to keep the laser moving forward without jumping around. If I'm not explaining this very well, and none of this is making any sense at all, then take a look at this kitten. Aw, how cute. Sorting the line segments into ordered paths was the first optimization that I had to do to the code. This helped cut down on overall time greatly, but the next optimization I needed to do was even better. You see, most of the output from the marching squares algorithm gives the same step size for every line segment. This means that no matter how smooth the actual data may be, the resulting contour line will have the same detail level as a much more jagged data set. In other words, there are more line segments than we really need for most of the shapes. And the algorithm we will use to remove the unnecessary segments is called the Raymer-Douglas-Poiker algorithm. It works like this. Given some set of at least 3 points that make up a path, look at the first and last point in the path and draw a line segment between them. Next, find the point between these first and last, which is the farthest away from the line segment. If the distance of this point from that line segment is less than some epsilon, we get rid of it. If the distance of this point is farther away from the line segment than that epsilon, we keep the point and run the same function twice.
The point to the last point in the set. This function will recursively look at all points from start to end. And Oh, but look at that kitten.
Okay, the next thing I needed to do was to spit all of this path data out into an SVG format. There's nothing too complicated here. I've already written functions for SVG output elsewhere, and so it really just comes down to doing it in a different syntax, Python. Oh, there's that kitten again. Aww. By the way, do not Google pythons and kittens. You've been warned. Okay, here we go. Alright, there you have it. This is the finished product. There is 50 sheets of paper in here, and each one took about 10 minutes, so this took me about a week, and that's not going to work. First of all, in order to do it faster, I think I can remove at least 30% of the sheets on the innermost detail, because you just can't see those layers anyway. So we can lose some layers and we can skip some layers, but I can also optimize these files. It took about 10 minutes per layer, and I think if I remove some of the data points and I do some more optimization, I can get that down. So we're going to get back in the code and we'll see if we can get this to run faster. Okay, after optimizing the code, this is the result. There's 26 sheets of paper in here, and to be honest with you, I can't really see any reason not to just take it lower like this. This is much better. Let's do some math here. The original one has 50 sheets, and each sheet took me about 10 minutes because it's just not optimized. And that came out to 500 minutes just to cut, plus about a minute per sheet to switch out the file, switch out the paper, and start again. So, all in all, this was about 10 hours of work, which ended up being 2 weekends and a bunch of nights, which borders on obsession. So this is not really realistic. This one, there's 26 sheets. Each one, the most complicated one, took 3 minutes and 24 seconds, and the last one took 52 seconds. So all in all, this was less than 45 minutes of machine time, plus again the minute per sheet for switching out, switching the file, getting the paper switched. So total, it was less than an hour and a half, all said and done. And I think it turned out pretty good. The colors are a little faded because it's not the same paper that I used in the old one, but that's okay. So now that I've got the optimization figured out, let's see if we can do some zooms and get interesting. This one's a little wild to look at. I'm not sure if I like this or the colors more. I think I'll do a rainbow one next. Let's try a Mandelbrot. Alright, so I've done this one backwards, so I didn't see it yet, so it's time for the big reveal. That's not bad. That's not bad at all. Cool. Alright.